Common and natural exponential functions. Hello everyone. Let's begin our discussion on common and natural exponential functions. To start, let's quickly recap what we have already covered. In the previous subsection, we discussed the general form of the exponential function, which is written as y equals b to the power of x in this general form. B represents any positive constant, provided that it is not equal to 1. In other words, for the function to be valid, b must be greater than 0 and not equal to 1. Now, while it is true that any value of b meeting those criteria can define an exponential function, you will find that in the fields of mathematics, science, and engineering, two specific bases are used far more frequently than others. These are base 10 and base e. In the upcoming slides, we will dive deeper into each of these, starting with the common exponential function, and then moving on to the natural exponential function to understand why they are so essential in practical applications. The common exponential function. Now, let's dive into the first of the two special bases I mentioned in the previous slide. When we use base 10, we refer to this as the common exponential function. Mathematically, this function is expressed as y equals 10 to the power of x. You might wonder why we use the term common here. This is because our standard numbering system is a decimal system, which is fundamentally based on the number 10, making this base the most intuitive for our everyday calculations. Because of this property, the common exponential function is widely used in various scientific fields to handle values that span several orders of magnitude. A great example of this is the Richter scale, used to measure the intensity of earthquakes, or the pH scale, which measures the acidity of a solution. Now that we have a clear understanding of the common exponential function, let's move forward and explore the natural exponential function. The natural exponential function. Now that we have covered the common exponential function with base 10, let us move on to the second most important base in mathematics, the natural exponential function. This function is expressed as y equals e to the power of x, while the previous function we discussed used a familiar whole number as its base. This one uses the letter e. You might be wondering what this e represents. It is a special mathematical constant that we will define in detail in the very next slide. What is the constant $? Now that we have introduced the natural exponential function, let us take a closer look at the base itself. The number e, which is known as Euler's number, is an irrational constant, much like the number pi that you have encountered in your study of circles. To be more specific, because it is an irrational number, e cannot be written as a simple fraction. This means that its decimal expansion continues infinitely without ever settling into a repeating pattern. While the digits go on forever, for our practical purposes and calculations, we use an approximate value. The number e is approximately equal to 2.71828. Mathematical definition of $. Now that we have established that e is an irrational constant approximately equal to 2.71828, let us examine how this number is actually defined mathematically. Mathematically, e is defined as the sum of an infinite series. This means that e is the result of adding together an endless sequence of fractions. The formula is expressed as e equals 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on, continuing indefinitely with 1 over n factorial. To help you better understand how this series works, let us calculate the first few terms. The first term is simply 1. The second term is 1 divided by 1 factorial, which equals 1. The third term is 1 divided by 2 factorial, which is 2 times 1, resulting in 0.5. And the fourth term is 1 divided by 3 factorial, which is 3 times 2 times 1, giving us approximately 0.1666. As we continue to add more and more of these terms, the total sum converges, or settles, toward the specific value of e. This is why the final value of e lies between 2 and 3. Understanding this mathematical foundation will be very helpful as we move forward to see how this constant appears in real-world continuous growth. Real-world application, continuous growth. Now that we have established what the constant e is and how it is defined, let's discuss why we call the function e to the power of x the natural exponential function. This function appears naturally in various real-world processes where growth occurs continuously, rather than in discrete or separate intervals. In other words, instead of growth happening in steps, like once a month or once a year, it happens every single instant. A classic and practical example of this phenomenon is continuously compounded interest, which we will examine in detail over the next few slides. Continuously compounded interest scenario. To set the stage for our scenario, suppose you invest a principal amount, represented by the letter P, at an annual interest rate, represented by the letter R in this context. P refers to the initial sum of money you are depositing into an account, while R represents the fixed percentage of interest you earn over the course of a year. Now that we have introduced the concept of continuous growth, let us apply it to a concrete financial example to see how it works in practice. This simple setup provides the foundation for the mathematical breakdown we will explore in the next slide, where we will see how the frequency of compounding affects the final amount. Step-by-step breakdown of continuous growth. Now, let's break down exactly how we arrive at the natural exponential function through a real-world scenario. Building on the investment example we just introduced, let's look at how the frequency of compounding affects your total return. First, let's consider annual compounding. If your interest is added only once a year, the final amount, A, equals the principal, P, multiplied by the quantity 1 plus the interest rate, R. However, in many financial systems, interest is compounded more frequently. If the interest is compounded n times per year, the formula becomes more complex. A equals P times the quantity 1 plus R over n, all raised to the power of n. This is where we see the mathematical magic of Euler's number. If we increase the number of compounding periods, n, toward infinity, which essentially means the interest is being added every single instant of every day, the expression 1 plus R over n, raised to the power of n, approaches the value of e raised to the power of r. Therefore, the final formula for the total amount after 1 year with continuous compounding is A equals P times e raised to the power of r. This is a perfect example of why the natural exponential function is the primary tool for modeling any process that grows continuously. Key takeaways. Now that we have explored the details of both functions and the concept of continuous growth, let us summarize the key takeaways from this section. First, we have the common exponential function. As we discussed earlier, this function uses base 10 and is expressed as y equals 10 to the power of x. It is particularly useful for measurements that span many orders of magnitude. Second, we have the natural exponential function. This function uses the base e, written as y equals e to the power of x. We call it natural, because it describes growth processes that happen continuously in the real world. Third, let's recap Euler's number, represented by the letter e. Remember that e is an irrational constant, approximately equal to 2.71828. As we saw in the mathematical definition, it is defined by the sum of an infinite series, specifically the sum of 1 over n factorial, where n goes from 0 to infinity. Finally, it is important to understand the significance of this constant. The function e to the power of x is the primary exponential function used in calculus. This is due to its unique properties during differentiation, which makes it much easier to work with than other bases when calculating rates of change. Keep these points in mind, as we will now move on to some common mistakes students often make when working with these functions. Common mistakes to avoid. To conclude our lesson, let us review some common pitfalls to avoid so that you can apply these concepts accurately. First, a very frequent mistake is treating the letter e as a variable, similar to how we use x or y in an equation. It is crucial to remember that e is a fixed constant value, much like the constant pi. Secondly, be careful not to confuse the common exponential function, 10 to the power of x, with the natural exponential function, e to the power of x. While both are exponential functions, they grow at different rates. Because e is approximately 2.718 and 10 is significantly larger, the function 10 to the power of x will increase much more rapidly than e to the power of x for any value of x greater than 0. Finally, when working with the infinite series we discussed earlier to define the value of e, please be mindful of calculation errors involving factorials. Ensure you calculate the factorials correctly. For instance, 3 factorial is calculated as 3 times 2 times 1, which equals 6, rather than simply multiplying 3 by 1.